let's take some more problems from the chapter laminar and turbulent flow. So let's take on this question. A steady laminar boundary layer is formed over a flat plate as shown in the figure. Okay, steady laminar boundary layer over a flat plate as shown in the figure. The free stream velocity of the fluid is u naught. Okay, the velocity profile at the inlet AB is uniform, while that at the downstream location CD, this section CD, is given by this relation. Okay, the ratio of the mass flow rate m dot BD, I mean mass flow rate through section BD leaving through the horizontal, horizontal section BD to that entering through the vertical section AB is. Okay, uh, it is a nice question, so I will recommend you to solve this question before seeing the solution. Okay, so if you have solved this question, let me tell you that like in this question what you have to do is you have to find the loss of mass flow rate through boundary layer region. Why? Because this loss of mass through boundary layer region will actually be going through this section BD. Why? Because of mass conservation, that m dot AB is equals to m dot BD plus m dot CD. Okay, so loss of mass flow rate through this section, through the boundary layer region, through this section will actually be going through the section BD. Okay, due to mass conservation. Okay, and the loss of mass flow rate through boundary layer region, we know that it is equal to rho u infinity delta star. Okay, rho is the density, u infinity is the free stream velocity, which is in this case it is given as u naught, and delta star is displacement thickness. Okay, this is displacement thickness. So this is actually the loss of mass flow rate through boundary layer region. Okay, and this mass will be exiting through section BD. Okay, so if we find this delta star, we can find the mass that is exiting through section BD. Okay, and one more thing I will tell you, that the displacement thickness, the definition of displacement thickness itself states that the vertical distance by which a solid boundary must be shifted to compensate for the loss in m dot due to boundary layer region. Okay, m dot is mass flow rate. So let's find out delta star, that is displacement thickness. You know, it is the relation is integration from 0 to delta. Delta is the boundary layer thickness, delta star is the displacement thickness, 1 minus u by u infinity. Here u infinity is u naught. Okay, so from this equation, u by u infinity is actually minus y by delta. Okay, so this is u by u infinity. We can put this equation, this relation here, and that implies delta star will be delta 1 minus 2y by delta plus y by delta all square dy. Okay, solve this. This will be equal to delta by 3. Okay, simple integration, you can solve this. So this is the loss in, I mean, so rho u not delta star, delta star is delta by 3, and this will be the mass flow rate, the loss in mass flow rate, or the mass flow rate leaving through section BD. Okay, so this is equal to rho u naught delta by 3. This will be the mass flow rate which will be exiting through section BD. Okay, and we have to find out the ratio of m dot BD to m dot AB, I mean the mass, which is mass flow rate which is entering. So the mass flow rate entering is rho u naught delta. Take the ratio, the answer will be 1 by 3, that is 0.33. So the concept was that the loss of mass flow rate in boundary layer region which will actually be exiting through the section BD. Simple mass conservation. Okay, next question. Consider a fully developed steady laminar flow of an incompressible fluid with viscosity mu through a circular pipe of radius r. Okay, the radius of the pipe is capital R, given that the velocity at a radial location of r by 2 from the center of the pipeline is u1, at a radial location of capital R by 2 from the center line of the pipe is u1. The shear stress at the wall is k mu u1 by r, where k is, okay, so k is a constant and that you have to find by using this given relation. Okay, so we know that u, that is velocity in a steady laminar flow through a pipe, is equal to minus 1 by 4 mu. Del p by del x is pressure gradient, capital R square minus small r square. Okay, so this is pipe, center line, capital R, it is the radius, and this small r is some radial location at which we have to find the velocity, or the velocity u1 is given here at r is equal to capital R by 2. Okay, so if we put small r is equal to capital R by 2 here in the relation of velocity, we get u is equal to minus 1 by 4 mu del p by del x square minus r square by 4. So this will actually be, this will be u1 now. Okay, because it is given that the velocity here is u1, so u1 is equal to minus 1 by 4 mu del p by del x, okay, 3r square by 4. Okay, this is the relation. Now what we have to find, we have to find the shear stress at the wall, and we know that again this relation we have derived already, you must have derived. So del p by del x r by 2, this is the wall shear stress. Okay, what we can do is we can find the value of del p by del x from this equation and put the value here, we will get wall shear stress. Okay, do this. So del p by del x is equal to, minus del p by del x is equal to 16 mu u1 by 3r square. Put this relation here. Okay, and what we get wall stress, wall shear stress, which will be 16 mu u1 by 3r square into r by 2. Okay, because we have to find the wall shear stress, so small r will be equal to capital R. Okay, solve it, you'll get, I guess, yeah. So now you have 8 by 3 mu u1 by r, compare it with k mu u1 by r. So k is 8 by 3, that is 2.67. 2.67. Okay, next question. For steady flow of viscous incompressible fluid through a circular pipe, again circular pipe, viscous incompressible fluid through a circular pipe of constant diameter, the average velocity in a fully developed region is constant. Yes, which of the following statements about the average velocity in the developing region is true? Okay, it increases until the flow is fully developed. Okay, we see that at the entry of pipe the boundary layer retardation increases. Okay, I mean, this is how the flow develops, and after that it develops. So we see as the flow enters, the boundary layer retardation takes place. Okay, and thus velocity keeps on decreasing until the flow is fully developed. Okay, so by this statement, I guess the option will be, it is constant and is equal to the no. It decreases until the flow is fully developed, it is constant but no. So the option will be C, that is it decreases until the flow is fully developed. Okay, because boundary layer retardation increases and hence the velocity keeps on decreasing until the flow is fully developed. Okay, so it decreases until the flow is fully developed. Next question. The velocity profile inside the boundary layer for flow over a flat plate is given as by this relation, where u infinity is the free stream velocity and delta is the local boundary layer thickness. If delta star is the local displacement thickness, the value of delta star by delta is. Pretty simple question. We know that delta star is equal to integration from 0 to delta 1 minus u by u infinity dy. Okay, all you have to keep in mind is that you have to carefully solve the integration. So delta star, that implies delta star is equal to 0 delta 1 minus sine pi by 2 y by delta, this is delta, okay, not 8 dy. Okay, so solve it. Delta star is equal to y plus cos pi by 2 y by delta upon pi by 2 delta, 0 to delta. Okay, so this will be equal to delta 1 minus 2 by pi. Take the ratio, the answer will be b, 1 minus 2 by pi. Okay, so this is delta star actually. Okay, so the answer will be b. So it was a basic question based on the formula, direct formula based question. Consider a laminar flow at zero incidence over a flat plate. Okay, a laminar flow over a flat plate is given at a zero incidence. Okay, the shear stress at the wall is denoted by tau wall, tau w. The axial positions x1 and x2 on the plate are measured from the leading edge. This is x1 suppose, and this is x2, as it's given that x2 is greater than x1 and they are the axial positions in the direction of flow. Okay, in this direction, suppose the flow is the fluid is flowing in this direction, so x1 will be, let x1 be of this length and x2 be of this length. Okay, so if x2 is greater than x1, then we have to find the relation between the wall shear stress at x1 and the wall shear stress at x2. And we know that for a laminar flow, the wall shear stress is directly proportional to x raised to the power minus 1 by 2, or we can say that it is proportional, it is inversely proportional to x raised to the power 1 by 2. Okay, so x increases, as x increases, tau will decrease. Okay, so tw1 will be greater than tw2. Match the options and get the answer. Okay. So next question. The viscous laminar flow, again the viscous laminar flow of air over a flat plate result in the formation of boundary layer. The boundary layer thickness at the end of the plate of length L is delta L. Okay, so the plate length is L and the boundary layer thickness has been given as delta L. When the plate length is increased to twice its original length, the percentage change in laminar boundary layer thickness at the end of the plate with respect to delta L is. Okay, again I have solved this type of question because I, I guess in the previous video the first question was from this relation, from Blazier's equation. We know that the boundary layer thickness is directly proportional to root of x. Okay, so let this be this proportionality sign be replaced by a constant k. Okay, okay, so percentage change will be k root 2 L. Okay, and minus L upon KL. This will be in root only. I mean, let me write it. Let me write again. So this will be k root 2l minus k root l upon k root l. Okay, so k cancels out, root l again cancels out root l. Okay, so this will be root 2 minus 1, that is 0.4142, and we have to find it in percentage. Okay, percentage, so that will be into 100, that will be 41.42%. Okay, so I've already told you that this relation is important, and many questions have been asked from this relation. Okay, so thank you.